In today's lesson, we are going to be looking at continuous versus discrete probability distributions. So we've already looked at discrete probability distributions before. That was the uniform distributions, binomial, and hypergeometric. But now we're going to make the shift to continuous. So just as an example, when a company fills an aluminum can with pop for sale, they print the milliliters on the side. Often the can is set up to fill up 355 milliliters. What is the probability that a pop can, which has been filled with 355 milliliters of liquid and advertises 355 milliliters of liquid, actually contains that amount? Right? So the machine is set up to distribute that much. It's advertised that that's how much is on there. What is the probability that it actually contains 355 milliliters? So just take a second to think about that. But if you really think about it, when we're talking about 355 milliliters, we're talking about exactly 355 milliliters, 0.0000000000, so on. So what is the probability of that actually happening? Probably very slim, because maybe there's an extra drop that falls in, maybe the machine isn't calibrated correctly, right? Puts a little bit too little, a little bit too much, right? Because how difficult is it to accurately program a machine to dispense the exact same amount every single time? So to get exactly that amount might be very difficult. So the probability might be very low because of what we're looking at, right? When we're looking at the volume, a measurement, which is continuous data, which is what we're going to be focusing on today. So again, going back over continuous versus discrete, we've talked about this multiple times, right? Continuous data is data that is obtained by measuring. Right? There's always a data point that exists between two data points, right? So if I look at between 1 and 2, there's 1.5. Between 1.5 and 1, 1.2. Between 1 and 1.2, 1.1, 1.05, 1.005, things like that. There's always another data point that will exist between two other points. It will be increasingly smaller, but there will always be a point in between. So there is the possibility that there is an infinite number of data points. And when we look at continuous data, we organize it into intervals. We think back to our histograms. Our histograms are in intervals, right, or ranges of data rather than specific amounts. So that's continuous data. Discrete data, which is what we've looked at before, is obtained by counting. Right? There's a finite number of data points, so there's a limited number, or there's a fixed number, and you don't have points between points. Right? So say, for example, you're looking at baskets made. In basketball, you have one basket or two baskets. You're not going to have 1.5. Right? It's 1 or 2 or 3 or 4 or 5, and so on. If we were to look at kind of an example, right? Discrete might be counting the drops of a water faucet or a water tap being open. A continuous version might be if we turn it on fully and just let everything, all the water rush out. Right? Might be an example like that. In terms of calculating probabilities, right, when we're looking at discrete probabilities, which is what we've looked at so far in terms of probabilities up to this point, it's determined by counting the number of successful outcomes divided by the total number of possible outcomes. Regardless of what the situation is, probability essentially boils down to that. Number of successful outcomes divided by the total number of outcomes. In a discrete probability histogram, each outcome has its own probability. Right? So 0, 1, 2, or 3. So it is still a histogram because the bars are joined together. There's no spaces, but it's not a histogram in the normal sense that we're used to. And we talked about that in previous lessons. When we're looking at continuous probabilities or continuous data, we don't just look at the number of successful outcomes divided by the total number of outcomes, right? Because there might be infinite number of possible outcomes. So what we do is we look at our histogram and we determine the probability by finding the area under the graph between the intervals. For example, the area of the bars under the graph will add to 1 or 100%. And it's really easy to kind of visualize this with a uniform distribution. And that's what we're going to focus on today. So we're going to focus on continuous probabilities looking at uniform distributions. So given the probability distribution histogram for wait times for a subway train that comes every 10 minutes, right? We have our histogram here. You could be waiting anywhere from 0 to 10 minutes. Now, we have our intervals, we have our bars. Each bar is 1, right? So basically the way it works is anywhere from 0 to 1 minute, you are going to be waiting in that spot, or that's how long you're going to be waiting. Anywhere 0 to 2, it's going to fall within there, or 1 to 2, 2 to 3, 3 to 4, 4 to 5, 6 to 7, 7 to 8, 8 to 9, 9 to 10. Right? So those are different ranges. Basically, any time a value will fall in there, or any time would fall into the different ranges from 0 to 10 minutes, right? We don't have to worry about accounting for the 7.5 minutes or 7.35 minutes or 7.035 minutes, things like that. Right? Again, it's uniform because we have kind of this box shape. Right? We have this box shape, so it is a uniform distribution. And we want to figure out, okay, what is the probability that the wait time will be 2 to 5 minutes? Well, if I look for 2 to 5 minutes, I am looking for the area underneath this section. Now, with uniform distribution, everything has an equally likely chance of happening. That is what is on our y-axis. So we can see our probability on the y. We can see that it is 0.1 or 10% chance of any time occurring. So there's a 10% chance of you waiting any specific time. So if I'm waiting, what's the probability of waiting for a time between 2 to 5 minutes? Right, I want to find the area underneath this curve, or underneath this line, which would essentially be the area of a rectangle. This rectangle here to be specific. So my area is length times width. Or in this case, my length is going to be 5 minus 2 times the width, which is our probability of 0.1. So we get 3 times 0.1, which equals 0.3, or 30%. So that means the probability of waiting anywhere between 2 to 5 minutes is 0.3. Now, what is the probability of waiting more than 6 minutes? Well, more than 6 minutes is going to be looking at the area underneath this box, or this line, or underneath this section of the graph. Right? So more than 6 minutes goes from 6 to 10. So we're looking for anything in this section. So if we're looking at that, then the probability of our outcome being greater than 6, our outcome is greater than 6. Again, we're finding the area underneath the graph, or underneath this line. We can find our width or our length, whichever one you want to call it, along the x. 10 minus 6, so that's a distance of 4, times the height, which is the probability, or 0.1. So we get 4 times 0.1, or 0.4. Therefore, the probability of an outcome, or a time, or waiting time more than 6 minutes is 0.4, 40%. what is the probability that a wait time is less than 2.5 minutes? So less than 2.5. So x is less than 2.5. Again, same graph. We're going to be going from 2.5 and downwards. So 2.5 would say is roughly here. So we're looking at the area under this section. Based on what we've done so far, let me just make it a little bit nicer. You're going to find the area underneath this graph, underneath this section, or the area of this section. So in this case, area is length times width for this rectangle. So we have 2.5 minus 0 to figure out the length along the bottom, multiplied by the probability, which is uniform for any wait time. 0.1, 2.5 times 0.1, 0.25. So therefore, the probability of having a wait time less than 2.5 minutes is 25% or 0.25. Now, what is the probability that a wait time is exactly 4 minutes? Well, 4 minutes is going to be exactly at this section. So I want to find the area underneath this part of the line. So if I go down and I look at that, well, the probability of exactly 4 minutes. Well, what is the length of that line? What is the length of that little rectangle? I'm at 4. I don't have a length, so it's actually 0. So 0 times the height is 0. So that means that the probability of waiting exactly 4 minutes is 0%. There's a 0% chance of it waiting 4 minutes. Now, why does that occur? Well, the reason that it occurs is because we're looking at continuous data. Right? And if you think of what is the probability of waiting exactly 4.0000000000000 and so on minutes, right? The probability is extremely, extremely low. You would practically call it 0. Now you might time and say, well, it waited 4 minutes, but that's only as precise as your measurement tool. In actuality, it might have been 4.1, 4.01, and so on. Right, so when you're looking at continuous data, right, the probability of getting an exact value is always going to be 0, just because of the nature of continuous data. So example 2, the Allenberg Bridge takes 20 minutes to raise and lower. Assuming the wait times form a uniform distribution, construct a probability histogram for this distribution. So we know what shape it has to be. Right? We know the shape has to be kind of this rectangle shape or this box shape. We need to figure out, okay, we know it's a uniform distribution. We know it's a 20-minute time to raise and lower or wait time. We need to figure out what is the probability. Well, let's kind of work backwards, right? And think about how we found the area from the previous ones. Right? We know the total has to be 100%. Or 1, right? So we know that has to be our total. So all the probability has to add up to 1 or 100%. So that means in my rectangle, the total area, again, we're finding probability, it's area, length times width. My total area has to equal 1. Area has to equal 1 because the total area under that rectangle is 100%, all the possible outcomes. Now we have to figure out, okay, how do I find my length and my width? Well, the length is the total possible time it could take. So I have anywhere from 1 or 0 to 20. So that means my length is 20 minus 0, and we usually multiply by the height, which would be our probability. So in this case, 20 minus 0 is 20, so 20 times whatever our probability is would give us 1. can kind of work backwards, solve the equation. 1 divided by 20 equals px, or the probability. So that means that that is the probability of this uniform distribution, or 0.05. So now when we go through and we draw it, it's going to be a box, and we can say, okay, this is about 1/5. So there's my uniform distribution. Each box is all the same, so that is my uniform distribution. Each one has each entire probability. It's a 5% chance across the board. So that's what our probability histogram would look like for this distribution. So what is the probability that you have a wait time between 5 and 10 minutes? So I'm going to go back, I'm going to draw in it quickly. So my probability distribution, so 0.05. So I want to find out what is the probability of me waiting anywhere from 5 to 10 minutes. So from here to here. So I want to find this area. Well, again, because the area, or the probability of it being between 5 and 10 minutes, is the area of that little rectangle that I've just colored in red, we have 10 minus 5 times the probability, which is 0.05. Again, we're finding the area underneath this graph, which is a rectangle. So 5 times 0.05, or 0.25. So that means that the probability of waiting between 5 and 10 minutes is equal to 0.25, or 25%. So there's a 25% chance you're waiting anywhere between 5 and 10 minutes. Now, there are some challenges when dealing with continuous variables, especially when we're looking at uniform distributions. In some cases, not all intervals are a width of 1. Right? So if we look here, we can see, okay, because our data isn't always starting from 0 and going up, right? Our range might be from 25 to 30, 30 to 35, 35 to 40, and so on. And there's an issue with that, right? Not an issue so much as more of a complication or a challenge. So if we talked about, if this is our distribution of data, it's a uniform distribution, we can clearly see that. And we can clearly see that it has a probability of 0.14. Maybe slightly higher, but for our sake, 0.14. So the probability is 0.14. So if I find the area underneath this box, it should equal 1, because the total probability is 1. Right? That's the total possible probability. So let's go through and quickly do that. The range along the bottom, 60 minus 25 times the probability, 0.14. We get 35 times 0.14. We get 4.9, which doesn't make sense. Right? So we clearly can't use those ranges because it doesn't make sense that we have 490% probability for all possible outcomes. The max is 100. So what needs to happen, if that's the case, we need to convert the intervals so that they are equal to 1 unit in width. So yes, even though our range is actually from 25 to 30, we need to account or convert it so that it stays, or it has a width of 1. So if we look at the bottom graph of what it's changed to, instead of starting at 25 to 30, 30 to 35, we go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. Now, it doesn't mean that we've changed what the range and values are. So if we're still asking for, say, 25 to 30%, we're going to look between these two. So it's still going to keep the same values. We're just going to relabel it a bit so that when we go through 0, 25, 30, 35, 40, 45, 50, 55. So we're just relabeling it to match so that when we go through and we calculate the area, right, of this entire uniform distribution, the area underneath, so now we have a range of 7, so 7 minus 0 times 0.14, we get 0.98, which is basically 1, right? So maybe it's a little bit above 0.14, but based on our graph, this is what we see, right? So we have to rename or convert the intervals, at least in terms of our graph, in terms of reading it, and start in width of 1, so starting at 0 and working our way up. They're still going to represent the actual times or the actual intervals, but for our purposes of like actually doing the calculations, we convert it to widths of 1. The other challenge is when we say less than or equal to, right? Because we've talked about looking at things like that, right? Less than 1 basket or less than or equal to 1 basket, things like that. So when you come across those situations, when you're talking about those two, right, you might say, okay, well, what do I do? How do I differentiate between less than and less than or equal to? Well, because we talked about the probability of being an exact value is 0%, then it really doesn't matter, right? Because I can say that the probability of something is less than or equal to 2, but because the probability of it equaling 2 is 0, it's the same thing as saying the probability of a value less than 2. Right? So if you see less than or equal to in continuous variables, it's the same thing. So you don't have to worry about, well, do I include the value? Do I not include the value? Do I go slightly above, slightly below? Because the exact value is 0, or the probability of any exact value in continuous data is 0, it doesn't matter when we refer to it as equals, less than or equal to, or less than, or greater than or equal to, or greater than. So the main thing from this lesson, or the key things, are looking at how we look or calculate the probability for continuous variables. It's different from discrete, right? So we have to find the area underneath the graph, underneath our probability distribution graph for a specific range of values, which is different from discrete data. And we'll look further at more, obviously, non-uniform cases, because if everything was uniform, then it'd be very easy, but the probabilities of events are not always going to be uniform. But we're still going to use the same concepts or same ideas. This was just kind of an easy introduction because it's a little bit easier to see or to calculate.